Hello, everyone. Welcome to the session on parallel and distributed machine learning. My name is Joseph Gonzalez. I will be the session chair. So we have 4 talks. 2 are 20 minutes and 2 are 10 minutes. We were going to try to leave a little time for questions at the end. If there's not enough time, you'll have to talk to the speakers at the poster or after the session. So our first speaker is Jia, who will be speaking about his work on exploring hidden dimensions and parallelizing convolutional neural networks.
Thanks for the introduction. Hi guys, I'm Zhihao. So today I'm going to talk about our work on optimizing parallelization for convolutional neural networks. So the computational requirements for training convolutional neural networks has increased dramatically over the last few years. So the left figure shows the number of layers involved in a convolutional neural network, which has increased from 12 layers to more than 200 layers. So the right figure shows the number of training samples involved in a training data set, which has increased from the original 60,000 images in Cipher 10 to more than 14 million number of images in the largest ImageNet 22K dataset. So in order to meet this computational requirement, it is now standard practice to actually parallelize the training onto multiple devices. So the most common parallelization approach is called data parallelism. The idea is to duplicate the entire model onto each device and assign disjoint training samples to this device. So each device will get partial gradients on these training samples. At the end of every iteration, device communicates with the parameter servers to synchronize the gradients. So an alternative approach is called model parallelism. The idea is to split the model into disjoint subsets and assign each subset to a dedicated device. So advantage of this approach is that we don't have to synchronize gradients because each layer is computed on a single device. But instead, you have to transfer tensors that goes across different devices. So one limitation with current approach is that they are trying to apply a single parallelization strategy, either data or model parallelism, to all layers. But we have found that actually data and model parallelism are not the most efficient strategies to parallelize a layer. And in addition, we also found that different layers in a network may prefer different strategies to achieve efficient performance. So in this talk, I'm trying to tackle 2 questions. First is how to efficiently parallelize a single layer. And second is how to efficiently parallelize an entire convolutional neural network. So in order to address the first question, we propose a search space of potential strategies to parallelize a single layer. We call it sparse search space. And to address the second question, we propose layer-wise parallelism that allow different layers to use individual parallelization strategies. So for the rest of this talk, I will first talk about the sparse search space and layer-wise parallelism. So they define a very large search space of potential strategies to parallelize convolutional neural networks. And second, I will talk about our graph-based approach to find efficient strategies. So it uses dynamic programming to reduce the search space. And after that, I will introduce FlexFlow, which is a deep learning framework we implemented to support layer-wise parallelism. And I will evaluate at the end. So first, let's talk about the sparse search space, which includes the sample, parameter, and attribute dimension to parallelize a layer. So the sample dimension describes how different samples are partitioned across devices, which has been used by data parallelism. So the parameter dimension indicates how different model parameters in a layer are divided across device, which has been used by model parallelism. And in addition, we can also use the attribute dimension that describes how different attributes within a sample are partitioned. For example, we can assign different pixels within an image to different devices to achieve parallelization. So this figure shows some example parallelization strategies. So for data parallelism, we only use the sample dimension to parallelize the training. And for model parallelism, we only use the parameter dimension. And the sparse search space also considers some more sophisticated parallelization approach, such as using the both sample and parameter dimension, or using a combination of all 3 dimensions to parallelize training. And by definition, we guarantee that different strategies in the sparse search space perform the same computation, and you can get the exact same result for every layer. And so one question you may ask is, why do we bother exploring this large search space instead of just using data and model parallelism? So there are 3 benefits I can provide. The first is that exploring the large search space can improve the runtime performance. So this figure shows the runtime performance for a convolutional layer and a fully connected layer. And if we only use data and model parallelism, we can achieve, that's the best performance we can achieve. But if we explore this larger search space, we are able to find some better parallelization strategy for these layers. And the second benefit is reducing communication costs. So this table summarizes the data we have to transfer by using different parallelization strategies. And as you can see that for some layers, using the sample or attributes dimension is much better than the parameter dimension. But for some other layers, using the parameter dimension achieves much better performance. So in addition, we also found that the degree of parallelism is another dimension. We should not use the same device for all layers. So for example, for different layers in the same model, actually they would prefer different degree of parallelism. So we define a layer-wise parallelism, which allow each layer to use any strategy in the sparse search space, and different layers can use individual parallelization strategies. And layer-wise parallelism guarantees that different parallelization strategy will perform the exact same computation and achieves the same network accuracy. So you don't have to worry about maintaining the network accuracy. You only have to optimize your runtime performance. So let's give some examples. So for this shows the data and model parallelism for the inception model. So for each square indicates a strategy for a single layer in the inception model. So the vertical dimension shows the sample dimension. So basically, in data parallelism, we just use the vertical sample dimension to parallelize each layer. So the right figure shows model parallelism. So the horizontal dimension shows the parameter dimension. So the model parallelism only uses the parameter dimension to parallelize layer. And this figure shows a possible parallelization among many others in the layer-wise parallelism. And as you can see that for some layer, we can use data parallelism. For some other layers, we can use model parallelism. And for some intermediate layer, we can use more sophisticated hybrid parallelism. And we can also use different degree of parallelism for different layers. So next, I will talk about how to find efficient strategies in layer-wise parallelism. So the main challenge is that layer-wise parallelism defines a very large search space. The reason is because the number of potential strategies we have to consider is exponential to the number of layers. So our idea here is to build a cost model to evaluate different strategies. So this can translate the original problem of finding efficient strategies to our optimization problems. And we can use dynamic programming to reduce the search space. So to formalize the problem, for each layer, we define a parallelization strategy SI to describe how the layer is parallelized. And SI includes an integer to describe the degree of parallelism for each sparse dimension. So for example, these are some examples parallelization strategies we have seen previously. And we can use three integers to describe different parallelization strategies in the sparse search space. And we use a global parallelization strategy S, which includes a strategy for each layer to describe one possible parallelization of the entire convolutional neural network. So with this definition, we build a cost model to quantitatively evaluate the runtime performance of a parallelization strategy S. So for each layer, our cost model first considers the computation time of the layer, which includes both forward and back propagation time. And these cost functions are measured from real executions. So for each layer, we also consider the parameter synchronization time, and this is estimated by the communication time to transfer data across different devices. And for each tensor, if the source and destination layer are on different devices, we also consider the data transfer time to transfer the layer from the source to the target device. And this is also estimated by the communication time. So to find efficient strategy, the question we are trying to answer is, do we really have to enumerate all possible strategies in layer-wise parallelism? So our answer is no, and this is based on an observation of strong locality in convolutional neural networks, because each layer in a CNN is only connected to a few layers with similar depth. So our idea is to iteratively reduce the computation graph by preserving the optimal strategies. And after that, we can just search the final, much smaller graph and iteratively reconstruct the original graph. So we provide two reduction operations. The first is called edge elimination. So if we can, in a computation graph, if we can find two edges with the same source and destination layer, we can actually remove these two edges and replace it with a new edge. And this will and this will maintain all optimal strategies. And the second reduction operation is node elimination. The idea is that if we can find a node with a single input and a single output tensor, so there are only 4 cost functions related to this layer. So therefore, for every fixed strategy of its input and output layer, we don't have to enumerate all possible layers for the intermediate layer. Actually, we can pre-compute the best strategy for every fixed input and output strategy. So this can allow us to remove this node from the graph. So we found that the node and edge eliminations are very efficient for reducing real-world neural networks. So this is the inception modular in Google's inception model. And I will show how we can iteratively reduce this complex graph to a simple graph with only 2 nodes. So here's how it works. First, we can apply the node elimination for all the nodes in the circle, red circle, because each of them is only connected to a single input and a single output layer. So we can actually remove them from the graph. And after that, we can remove the redundant edges in the red circle. And after that, we can perform another round of node elimination by remove the nodes in this red circle, because each of them is also connected to a single input and a single output tensor. And finally, we can get a simple graph with only 2 nodes. So once we found, and it is much easier to find an optimal strategy for this final graph because it only has 2 nodes. And once we found a strategy for this final graph, we can iteratively reconstruct a global optimal strategy for the original graph. So we compare against our approach with a depth-first search baseline. Recall that our approach first reduced the original graph, search for the final graph, and then reconstruct the original graph. And we can always find a global optimal strategy under our course model. So a baseline is use the depth-first search plus A star to optimize to search on the original graph. And this table summarizes the execution time of different search algorithms, and you can see that our approach achieves orders of magnitude speed up compared to the baseline depth-first search. And we also provide a much better theoretical time complexity guarantee. So next, I will introduce FlexFlow, which is a deep learning system we built to support layer-wise parallelism. So our motivation is that supporting layer-wise parallelism in existing deep learning frameworks requires significant efforts. So you have to manually partition every operator to tasks. If you would like to implement layer-wise parallelism in TensorFlow or PyTorch, this just requires significant amount of changes. So to make it easier to realize layer-wise parallelism in real-world systems, we built a distributed deep learning framework that can support any parallelization strategy in layer-wise parallelism. And FlexFlow is built using the Legion task model, and we provide the similar APIs as existing deep learning frameworks. So the left code snippet shows defining the net 5 in FlexFlow, which is very similar to the PyTorch interface. And in addition, a user can also provide a configuration file to describe how each layer should be parallelized. And as you can see that you can use any single layer or a combination of different layers to parallelize any layer. And you can also use different number of GPUs for different layers, which is very flexible. So that's why we call it FlexFlow. And next, I will talk about our evaluation. So the first baseline is, of course, the most commonly used data parallelism approach. So we run data parallelism experiments on TensorFlow, PyTorch, and FlexFlow. And we found that FlexFlow always achieves better performance than TensorFlow and PyTorch, which means our implementation of FlexFlow is optimized and efficient. And so the next baseline is model parallelism, and which always use the parameter dimension to parallelize all layers. And we also compare against a human expert designed approach, OWT parallelism. So the idea is to use data parallelism for convolutional and pooling layers and switch to model parallelism for fully connected layers. So this is also considered as a baseline in our experiments. And finally, we evaluate layer-wise parallelism and always use an optimal parallelization strategy found by our search algorithm to parallelize the actual executions. So this figure summarizes the training throughput achieved by different approaches. And as you can see that layer-wise parallelism always achieve better performance than other state-of-the-art approaches. And so the right curve shows the theoretical upper bound, which means theoretically what's the maximum throughput we can achieve by using this number of GPUs. And as you can see, that layer-wise parallelism can help bridge the gap between the theoretical throughput and the ideals and the actual throughput we can achieve in real-world systems. And we also found that FlexFlow is very efficient at reducing data transfers in distributed executions. So this figure shows the total amount of data transferred per iteration by using different parallelism. And as you can, so for these figures, the lower the better. And as you can see that layer-wise parallelism can significantly reduce the communication cost compared to other approaches. So we also performed a case study on an optimization strategy found by our search algorithm for parallelizing the inception model on 4 GPUs. So again, the vertical shows the sample dimension. The horizontal shows the parameter dimension. And so for all previous layers, the best strategy used data parallelism for beginning layers. The reason is because at the beginning you have large tensors, but very small amount of parameters. So using data parallelism is much better. So as the depth of the network increases, so the tensor size decreases, but the number of parameters increase. So the layer-wise parallelism switched to a mixture of multiple parallelization strategies for the final layers. And this can help achieve better performance than other state-of-the-art approaches. So to summarize, the main takeaway I'd like you to bring is that we believe exploring the search space in layer-wise parallelism can find better strategies than state-of-the-art approaches. And we have also open sourced our FlexFlow implementation, and we hope this can facilitate future research. And our post session is tonight at Hall B, number 34, and hope to see you guys tonight. Thank you.
Time for a few quick questions.
Thanks for the talk. So I have 2 questions. One, did you consider convolutional networks like ResNet that don't have very fully connected layers? Mm-hmm. Because it seems the model parallel part was mainly helpful for AlexNet or similar networks that have a lot of fully connected networks. So that was my first question. And second one is, why do you need to solve an optimization problem for this? Because you should be able to analytically compute whether model parallel is better than data parallel by looking at the communication volume.
Right, so to answer your first question, we also found that for ResNet, the improvement space is not that big. So for AlexNet, we can achieve 3 or 4 times speed up, but for ResNet, it's only like 10 to 20% speed up. And so the main reason is because ResNet has already tried a very good job at reducing the number of parameters in each layer. Right. So for the second question, so our cost model considers both the computation time to actually run the layer on devices, and also as well as the communication time to transfer data between devices. And to model the communication time, we assume a fully utilized channel bandwidth. So we assume that the time to transfer data is proportional to the amount of data being transferred. So it is also considered as in our cost model.
Okay. Thank you.
Thanks.
I have just let's call it a simple question.
Mm-hmm.
All of this relies very much on actually having good numbers for those costs that you have for the inter-device communication and so on and so forth.
Right.
And these things are very much subject to change with what we see here, right? There's like lots of new devices coming out and lots of developments in this area.
Mm-hmm.
So how do you want to account for that over time? Yeah, because you might do like a very nice FlexFlow framework and people start to use it, but things may change very fast. So how can you take that into account?
Right. So we believe that FlexFlow is, so we have assumption in our paper, which is that the computation time is irrelevant to the data. So meaning that we perform the same computation on different images, they should have the same computation time. So we have this assumption. So that's why we can measure the computation time at the beginning, and we don't have to worry about the exact real executions. So this is true for most neural network operations because they are based on dense matrix multiplication. So that's true for them, but not true for some other applications, such as some graph traversal applications. So that's also one limitation with FlexFlow. So we must assume that the computation time is irrelevant with the data being computed. So, and we can pre-compute all the computation time.
All right. thank our speaker one more time?
Yep, thank you.
All right, so our next speaker is Jiangzhang Wu, who'll be speaking about, if she gets it up. Go ahead and start.
Thanks for the introduction. Hi everyone, I'm Jiaxiang Wu from Tencent AI Lab, and today I'm going to talk about our error-compensated quantized SGD and discuss how it can be used to speed up large-scale distributed optimization. So let's start. Let's begin with distributed optimization. A common setting for distributed optimization is that we use data parallelism. In this setting, the dataset is divided into multiple subsets and then distributed stored at multiple nodes or workers. Each worker then keeps a full copy of the model parameters so that for any input, each worker can independently compute its corresponding gradient. For data parallel-based distributed optimization, model parameters can be updated in the following way. In each iteration, all the workers first randomly select a mini batch of training samples and then compute the local gradients and then broadcast them to all the other workers. Whenever a worker receives all the local gradients sent by other workers, it can compute the average of the local gradients and then use it to update its model parameters. So the time consumption can be roughly divided into two parts, computation and communication. The communication of overhead mainly comes from the gradient communication. So it is proportional to the number of model parameters and the number of workers. So it may become the performance bottleneck for large-scale distributed optimization. I will first quickly review some of the existing works on gradient compression, which is to compress gradient so that we can reduce the communication overhead. The first part is binary quantization, which is to quantize each component in the gradient to either 1 or -1 based on its sign. The second part is ternary quantization, which uses an extra quantization point, which is 0 to encourage sparsity so that we can achieve higher compression rates. The third part is multi-bit quantization, which is to use more quantization points to offer more fine-grained quantization so that we can reduce the quantization error and ensure more stable convergence. Besides quantization, there are other methods that use gradient specification, which is to, in iteration, we only transmit some of the gradient to other workers, but not all the gradient. The basic idea of our proposed error-compensated quantized SGD is also similar to the previous gradient compression methods, which is to quantize local gradients before transmission, so that the communication overhead is smaller. What is different from previous work is that we introduce an error feedback scheme to export the information lost in the previous quantization procedures. Let's first consider the distributed optimization scenario. In the first iteration, we have the model parameters W0, and each node selects a mini batch of training samples and compute the local gradients. And then the average of local gradients can be computed to update the parameters so that we have W1. And this procedure is repeated until we have a converged result. The computation of in this process, the computation of the average gradient requires that we must transmit exchange gradient between all the workers, so that we can use gradient compression to speed this part up. So here before we exchange local gradients between all the workers, we first compute a quantized version of it, namely the G tilde. The quantized gradient is more efficient to communicate because we can add some more constraint on it, and the average gradient can be computed on the quantized gradient instead of the original full precision gradient. But this will also introduce a new problem because the quantization procedure will introduce extra noise to the gradient signal. And this extra noise will, it is possible that it will slow the convergence down and even lead to divergence. So coming next, we will introduce the error feedback scheme to address this issue. Specifically, when we quantize local gradients at each worker, we not only just compute the quantized gradient G tilde, but also we compute the quantized error epsilon here. And we will accumulate it through all the iterations. In the next iteration, when we quantize the local gradients, we not just use the current local gradient, we also add the previous accumulated quantization error to the current local gradient and use it as a compensation term. And we discover that this error feedback scheme will provide more stable convergence behavior in the practice. Now we will introduce how the local gradients are quantized in our method in details. Here we use the quantization function QS for gradient compression, where S stands for the number of non-zero quantization points. In this example, we have S equals to 4. The quantization function consists of 3 parts. The first part is sign, and followed by scaling factor and the quantization level. Overall, this quantization function will provide an unbiased estimation of the original vector V. The quantization level is computed as follows, which is given by the equation in the bottom of this slide. It is computed as follows. We first normalize the absolute value of Vi and divide it by the scaling factor. And we will choose a quantization point based on this normalized value. For example, if the absolute value of Vi divided by the scaling factor equals to 0.55, then it will be quantized to either to L equals to 2 with a probability of 0.8, or quantized to L equals to 3 with a probability of 0.2. So this will be an unbiased estimation of the original V. Now we introduce the error feedback scheme, which in every worker, we will maintain another H variable to accumulate all the previous quantization errors. Here we use a time decaying factor beta here. The accumulated quantization error is initialized with all the errors and then updated in each iteration using the current quantization error, the difference between G and G tilde. The error feedback scheme is adopted in the quantization function. So instead of just feeding the current local gradient into the quantization function, we also add the accumulated quantization error H here and use alpha as a hyperparameter to adjust the trade-off between the current local gradient and the accumulated quantization error. So after the gradients are quantized, we can encode it more efficiently than the original 32-bit full precision gradient. Here we use D to donate the number of parameters in the model. So for the original 32-bit full precision gradient, we will need 32 times D bits to encode it. After quantization, we have only 2 times S plus 1 possible values for the quantized gradient. So we can use 32, this is for the scaling factor, and D times R, this is for the H quantized component. This will be much smaller than the original 32-bit full precision gradient. And furthermore, we can also use entropy encoding methods, for example, Huffman encoding, to better exploit the data distribution after the quantization because it will concentrate on some of the quantization points. Here is the overall is a summary of our compensated quantized SGD method. So in the first part, we compute the gradient and quantize it, and then do the communication. And in the second part, we use the quantized gradient to do the model update. So far, we have presented our algorithm, and so in the next following slides, we will analyze its theoretical guarantees on the convergence behavior. Here, we first we introduce the results presented in the QSD paper, which is published in the last year NIPS. Basically, it says that if the gradient we used to update the parameters have some random noise, and the variance bound is given by the schema squared, then the suboptimal gap after t iterations will be bounded by this inequality. And from this inequality, we know that if the variance bound is smaller, then we will arrive better convergence. So we compare the variance bound between QSGD and ECQ SGD, which is our method. We note that it is worth noting that QSGD is actually a special case of our method when we set alpha to zeros, which is to disable the error feedback scheme. Here we use two assumptions. First one is that local gradients are true gradients, so that we are doing gradient descent instead of mini-batch stochastic gradient descent, so that only the quantization error will contribute to the random noise in the gradient. The second assumption is that local gradient's second moment is bounded by the constant b here. This holds for both algorithms. So for the EQSGD, we note that its variance bound is given by gamma times b, where gamma depends on the quantization function. D is the number of parameters, and S is the number of non-zero quantization points, and B is the variance bound of the second moment bound of the local gradient. And for the ECQ SGD, we have the following result. As you can see, it is slightly larger than the QSGD's variance bound. This is due to that we use the error feedback scheme here. So previous quantization error will also contribute to this. But with properly chosen hyperparameters, we will ensure that this will not be much larger than the QSGD. And by substituting this variance bound into the previous theorem, we'll have the similar convergence rate for ECQSD, but with a slightly larger constant factor than QSGD. So the above analysis is based on the assumption that the objective function will try to optimize is convex without other special constraints. Now we limit our discussion to convex quadratic optimization, which is given by Fw equals to this equation. We have this theorem on the worst-case error bound of ECQ SGD algorithm. On the right-hand side, we have 4 terms, and the first two terms does not depend on the quantization function, and is the same for both the QSGD and our ECQ SGD. So we just leave it as it being. And for so the main difference lies in the last 2 terms, especially in the last one, which is the previous quantization error's contribution to the final error bound. Here, epsilon t is the quantization error bound quantization error introduced in the tth iteration, and theta t is a corresponding multiplier. For QSGD, the multiplier will only have the first term, but not the second term, because alpha equals to 0. So let's first consider the multiplier of the previous quantization errors contribution. We have this number, which indicates that with the properly chosen hyperparameters, the multiplier in each QSGD will consistently precede its counterpart in QSGD. The basic idea is that the error feedback scheme adopted in our method will lead to that the quantization errors contribution will be canceled out across iterations. And next, we compare the upper bound of previous quantization errors contribution to the final error bound. We have this number, which indicates that with properly chosen hyperparameters, ECQ-SGD can better suppress previous quantization errors contribution in the final error bound than QSGD. So in conclusion, at least for convex quadratic optimization, ECQ-SGD will have a tighter worst-case error bound than QSGD. Following are some highlights of our evaluation results. We first perform experiments on linear regression models to validate our previous analysis on convex quadratic optimization. We carry out experiments on 3 synthetic datasets with different number of feature dimensions, which is noted in the dataset name. From the first row, we discover that ECQ-SGD converges faster than QSGD for all datasets and achieves better solution after convergence. From the second row, we note that the suboptimal gap of our method is smaller than QSGD, which matches our previous analysis. Following is decompose the time consumption of our ECQSD and QSD and together with 32-bit full precision SGD. We see that for both the QSD and ECQSD, since the gradient is compressed, the communication time is largely reduced, even taking the encoding and decoding time into consideration. Another observation is that ECQSD can use a relative coarse quantization function to achieve similar performance as the vanilla SGD, but QSGD will require more fine-grained quantization. Following is our experiment on non-convex optimization, which is to train a ResNet 20 model on the CIVA 10 dataset. On the left, we plot the loss functions value versus the number of iterations of various gradient compression models. We see that our ECQ-SGD method converges similar to the vanilla SGD and arrives at the similar test performance. And on the right hand, we have the comparison on the gradient compression ratios, and our method can achieve about 18 times compression in the gradient. Next, we use a performance model to evaluate our ECQ-SGD method. We have the following hardware specifications, and we see that ECQ-SGD will have a clear advantage over the vanilla SGD. And this is the parameter study. So in short, we need to set a practice. It is recommended to set beta to 1 and alpha to a relatively small value, so that because if alpha is too small, ECQ-SGD will degenerate to QSGD, and if alpha is too large, the constraint will be violated. So some takeaway messages. First, local gradients can be compressed to speed up, and the usage of accumulated quantization error improves the convergence. Thank you. And this is our poster, and if you are interested, please stop by our poster tonight. Thank you.
for a few quick questions.
Hello, thanks for the talk. Do you know whether a linear distribution of quantized values is better than a logarithmic distribution of quantized values?
Could you repeat your question, please? Sorry.
Well, having decided that you can afford a few bits in each of your quantized values, is it better to distribute the values represented by those few bits linearly or logarithmically? Because when you compute the full precision gradient, you're computing them with floating point, which is obviously a logarithmic distribution. But if I understood correct, you're then quantizing to a linear distribution. Do you do that deliberately?
We did not try to use the logarithm, and I think that would be our next trying point to improve the performance. Thank you.
Since there are no other volunteers, could I ask another question? Your error compensation scheme, to me it looks the same as Frank Sider's scheme in the 1-bit SGD paper from 2014. Is it actually different? Given that that's a 1-bit and yours is n-bit, I get that. But
yeah, in the 1-bit SGD, they only, as far as I know, they only use the last iterations quantization errors for compensation. And we noticed that we use more iterations, it will help better. Thank you.
Let's thank our speaker one more time. So our next speaker is Thomas Monroe, who will be talking about DICOD, Distributed Convolutional Coordinate Descent for Convolutional Sparse Coding.
So, hello everyone. I'm very happy to be here to talk about DICOD, a distributed coordinate descent algorithm for convolutional sparse coding. So in this work, we consider the convolutional dictionary learning model, which try to encode a signal X as a sum of convolution between patterns dk with coding signals zk. So this pattern dk typically encodes some recurrent patterns in the time series, and zk typically encodes the localization of these patterns. And this can be very useful to study physiological time series, for instance. So one part of this model, which is very computationally expensive, is the convolutional sparse coding step, where you're given a signal x of length t, and a fixed dictionary of k patterns of size w, which are typically way smaller. And you want to find the coding signals associated to this signal x. So you want to find z, which is k signal of size L, where L is where L is equal to t minus w plus 1. And typically, to solve this problem, you need to solve a convolutional lasso. So the convolutional lasso is composed of two parts. The first part is the data fit term, which measure how well you're reconstructing your signal with the sum of convolution. And you have a second term, which is sparsity-inducing regularization, which here is the L1 norm. So there exist many classical algorithms to solve this problem, such as the coordinate descent, the FISTA algorithm, or the ADMM-based algorithms. But all those algorithms tend to not scale very well when the length of the signals explode, which is the case for many applications, especially for neuroscience data sets. So if we look more precisely to the coordinate descent algorithm, what this algorithm does is at each iteration, it selects a coordinate with either a fixed policy, so saying, for instance, a cyclic selection or random selection, which are computationally, which scale constantly, which has a constant computational complexity, sorry. Or there is also another policy, which is the greedy policy, where you select at each iteration the best coordinate that you can update. But this policy is more expensive because it scales linearly with the length of the variable that you are trying to optimize. Then once you have selected this coordinate, you can update its value. So in the case of convolutional coordinate descent, you can actually compute the optimal value of this coordinate given that all the others are fixed. And you can do it efficiently with a complexity of kW, which is typically the size of your dictionary. And this update is a very local update because it only impacts a time segment of twice the size of your dictionary atoms. So the idea to speed up this algorithm would be to try to match the computational complexity of the coordinate selection with the complexity of the update. So to do that, what you can do is to try to select the coordinate locally greedily. So the idea is if you divide the signal you are trying to optimize in m subsegments, then you can select greedily the coordinate that you want to update in each of these subsegments. And if you choose the number of subsegments that you consider in a nice way, so if you just select m to be L divided by the size of your dictionary, then both parts of your algorithm will have the same computational complexity. So the nice thing about this algorithm is that it can be distributed pretty efficiently, because you can basically say that you have m worker, and each of the m worker will be responsible for the updates on a subsegment of your signal. And as we have seen, when the update is when you select a coordinate which is intern to this subsegment, the update will be independent of all the other workers. So you can have an asynchronous setting. The main issue is if the selected coordinate is on the border of your worker, then you need to have some kind of communication to ensure the convergence of this algorithm. So this can be done pretty efficiently by only sending the coordinate number that you're updating and the value of this update. Then with this communication, the algorithm continue to converge. But if you are in an asynchronous setting, the main issue is if you have interfering updates. So that is to say, if two neighboring cores are both updating a coordinate in the border region. Then the two influence of these updates overlap, and you have an indetermination area in this, which is this gray area. So what we show in our paper is that even with these interfering steps, the convergence of our algorithm is guaranteed, and you can run this algorithm in an asynchronous setting to obtain the solution of the convolutional lasso. We also show that this algorithm enjoys a superlinear speedup. That is to say that if you double the number of cores, you are going more than twice as fast. This is due because you have two sources of acceleration. The first one is you're using more cores to update, to perform your updates. And the second one is that you also, when you're increasing the number of cores, you're also reducing the complexity of each iteration because you're considering a subsegment which is smaller. So we compare this algorithm with a different state-of-the-art algorithms. So here you can see FISTA and FCSC in yellow and black, which are full gradient methods. And in red and green, you have a coordinate descent algorithm. So the red one is the greedy coordinate selection, and the green one is the randomized selection. And in blue, you can see DICOD with 60 workers. And what we can see here is that the fact that we are using 60 workers and locally greedy updates does not change much the convergence property of our algorithm, because the two curves are pretty close, and the difference are only due to the fact that we are only taking locally greedy updates and that there are some interfering updates. And if you look at the convergence in time, obviously the DICOD algorithm with 60 workers is using more computational power and it's going way faster. But what we show in the paper is also that if you use this locally greedy scheme even sequentially, you can also accelerate the resolution of such an algorithm. So it's pretty interesting, even if you don't want to run it in a distributed setting. Then we also analyze the the scaling of this algorithm with the number of code. And we were also able to prove the fact that this algorithm was scaling super linearly. And when you have a low number of core compared to the size of your problem, you even speed up quadratically. And at some point you have some limitation that slow down the scaling. So what we proposed in this algorithm is an efficient asynchronous distributed algorithm, which have efficient communication and which leverage the structure of our problem to solve it faster. And it has also no exogenous parameters, so you don't need to fix the learning rate in a precise way to be able to converge. So thank you for your attention, and if you want more details on this, come to my poster number 33, and allez les bleus!
All right, so we have time for possibly one very quick question. I have a very quick question. So you got superlinear scaling. Can you talk about why?
Yeah, so the reason why the superlinear scaling is appearing in this is that the fact that when you increase the number of core, you increase the number of work you can do. So this is mainly the reason why you have a speed up in most distributed algorithm. But here, when you also increase the number of core, you're also reducing the complexity of each iteration. The reason why this algorithm has a superlinear speedup is because the iterative algorithm that we took at the beginning is non-efficient. If you take the sequential algorithm and you apply the same idea of selecting locally greedy your updates, you will still have a speedup. So this, basically the superlinear speedup is the reason why we realized that we could run this algorithm sequentially and get some speedup. So yeah.
All right, make our speaker one more time. All right, so our final speaker in this session is Zhengyuan Zhao, who's going to talk about distributed asynchronous optimization with unbounded delays. How slow can you go?
Well, thank you for the introduction, and thank you all for staying. I realize I might be the last obstacle that stands in the way between you and lunch, so I'll try to be on time. So really, this is this. By the way, there's no. Just want to say outside, there's no neural network in this talk. So if you, yeah. So, okay. So this is what this is really just a simple piece of theoretical work that aims to achieve a qualitative understanding about distributed asynchronous stochastic gradient descent, which is one of the most widely used first-order algorithms nowadays, and to understand when you get global convergence. Okay, so that's sort of a one-sentence summary of what this is trying to do. Okay. Okay. Interesting. This is my first time using Mac, so this is okay. I guess we'll just go with the flow. So let me maybe skip the marketing slides, just given that this is a distributed optimization crowd. You probably have seen this many, many times. So our starting point is just stochastic optimization. Very generically, stochastic optimization problem looks like you're taking an expectation of some random function. X is your decision variable. Omega is underlying randomness. And here, assuming that X is a compact convex set. And a canonical example. Wow, this is really painful. Canonical example of this is essentially empirical risk minimization, which is a average of the sum of x fi's, where each fi is the cost associated with the ith example. And as you guys all know, stochastic gradient descent is sort of the main method that's used to solve this kind of problem. And when you have a lot of data and the scale is large, you typically do this on some distributed computing architecture. And depending on the computing architecture and how you parallelize stochastic gradient descent, you would get distributed stochastic gradient descent, which is a family of algorithms that have many different variants, and depending on how you parallelize it. And typically, we go with asynchronous stochastic gradient descent because in practice it's just hard to enforce synchronicity when you have a lot of computing nodes and workers that are heterogeneous. I think this just should all be kind of familiar to you guys. So here, I guess the first one is the master-slave model, where essentially, just to quickly, just a slave, okay, let's not use the word slave. So a worker has essentially draw a subset, a sub-batch of the training example, computed gradient, sent to the master, and then the master does the update. And then in the right-hand side, so that typically corresponds to data center, and the right-hand side is sort of multi-core processor, which corresponds to the GPU setting where each processor just asynchronously updates, draws a sub-batch of the data, computed gradient, and then update the global model. So I think, so these are the two mostly common used computing architectures, and then you will get slightly different algorithms exactly depending on which one you use. So I guess it's sort of I guess our focus here is going to be on the first one, the master-slave. I think everything still goes through with with some modifications depending on exactly what you're trying to do. But here's sort of a common abstraction, algorithmic abstraction of the algorithm, just distributed asynchronous stochastic gradient descent, essentially is, the core feature here is that the delayed gradient, right? By the time the local worker updates the gradient, the global parameter may have already been updated by other workers many, many times, and that's sort of common no matter what distributed computing architecture you have. So just a little bit notation. So n is the it's a global counter, and Sn is the sort of the, so n is the current iteration, Sn is the previous iteration from which the gradient is generated, and Dsn is the delay associated with iteration Sn. That is, at Sn, iteration Sn, how many more iterations do you need before the gradient gets accepted, gets received? And then you do a projection. And here the way we're doing projection here is a lazy projection, okay? It's sort of like a dual averaging scheme, because there's a global y, which is a dual variable that accumulates gradient, and then you project that to the primal variable xn. Okay? So there's a lot of work in this space depending on the architecture, depending on the specific variant of algorithm, depending on assumption you make. I'm not going to be able to list all of them, but roughly speaking, what's relevant here is essentially in terms of the convergence guarantees you get. Typically, people look at convex functions, and they assume bounded delays, and they get some, in that case, you get convergence to global optimal. And there's some work, there's one paper that's on non-convex objectives, in which case you get the average criticality gap vanishes, again, under bounded delays. Okay, so again, as I said at the very beginning, what we want to look at is what is, the sort of the broadest set of conditions under which we can be guaranteed with global optimality convergence. Okay, so we're going to look at it from sort of three aspects. One is, we're going to look at a class of functions, not necessarily convex. And the other feature is large delays. Okay, so all the previous work is on bounded delays, essentially for stochastic optimization. But in practice, I guess I skipped the first two slides when you have the volunteer computing, which is all the nodes are just normal users, and they participate in the distributed computing architecture on and off. It's very easy for a computing node to get saturated, and so how much delay can it tolerate, right? So in this case, the delay can grow as a function of n, I guess here, as a function of the iteration. Okay, so what about in that case, what about the large case delay? And what is the sort of the strongest convergence guarantee that we can get? So this is what I mean at the very beginning about a qualitative understanding about convergence. Under what sort of set of conditions do we, what is sort of a picture about, convergence in this distributed setting? And here's sort of the main assumption we make. First one is just a regularity assumption that's pretty common if you open a normal paper in this space. The first one is always this, differentiable, bounded second moments. I guess you probably had a lot of those, seen a lot of those things. And the second one is this class of functions called variational coherent. There's a lot to be said about this class of functions, but I'll just mention that it includes convex, strictly includes convex, pseudo-convex, star convex. Many others as well. Here's a few pictures that look relatively nice, I guess. They're colored. So the last one is the Rosenbrock benchmark function, which is pretty non-convex. The middle one is x1 squared, x2 squared. Anyway, so yeah. As I said, there's a lot to be said about this, but this is essentially just a class of functions. And what's the main takeaway? I have 1 minute. So here's the class of delays that it can tolerate. It depends on, and the message is that we can do polynomial. Okay, so bounded delay is one of the, I guess, the first one, and then beyond that is sublinear, linear, and polynomial, which effectively, I would argue that's kind of pretty much anything in practice, right? You could, of course, you could also have exponential, but which is not part of our result, but what is it? Yeah. Anyway, it probably doesn't exist in practice. So in that case, we get under the regularity assumption and under variational coherence, if we use the step size according to this table. In particular, when we have polynomial growing delays, we need to use 1 over n log n log log n. Then the last iterate, xn, converges to the global set of global solutions with probability 1. Okay, so and you might think that if we have exponential delays, then 1 over n log n log log n log 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 n would work, but it doesn't. Anyway, so that's just a side point. Okay, so I guess with that, I'll just stop here then, since I'm out of time. Yeah, I am. So any questions?
So we are out of time, so maybe you can get some questions after
Sure.
over lunch.
Yep.